Yeah, it's our pleasure to have like Joseph to talk about his work in our seminars. And today he'll be like talking about how can we utilize the quantum contextualities and trying to show them some separation between like classical and quantum machine learning algorithms. And perhaps this will kind of serve as a bridge for us to kind of like go and look on quantum foundations and see what can be extract from them and trying to apply it to or extend it to quantum machine learning and trying to identify some kind of like advantage over there. Joseph, maybe you can like start sharing your screens and the floor is yours.
Sure, thank you. Okay, so you can see and hear me well, I assume. Okay, cool. So yeah, thanks very much for inviting me to speak at the seminar. So my name is Joseph Bowles. I'm a QML researcher at Xanadu, and I'm going to present this recent work entitled Contextuality and Inductive Bias in Quantum Machine Learning. And this is my first work in quantum machine learning. Before that, I was basically in quantum foundations for a long time. And so really this work is an attempt to bridge a bit what I was doing before, which is very much related to contextuality, and what I'm doing now, which is quantum machine learning. And I'm going to spend most of the talk trying to explain a sort of connection that we found between these two fields. And that connection is from this concept of inductive bias, which you've maybe heard about in machine learning, to a concept called operational equivalence, which is sort of a very important concept in contextuality. So I really want to try and explain that link. And once I've done that, the sort of implication will be that we can see how contextuality has an effect on the expressive power of learning models, and in turn, this can affect learning, which I'll talk about as well. Okay, so yeah, I want to start with what is potentially a very obvious statement, but I think it's sometimes overlooked, and that is that the performance of a learning model typically depends on the ability of the model to encode a structure which is present in the data. Okay, so to give a very simple example, let's imagine we have just 1D data, and let's say this data satisfies some approximately linear relationship, and let's also say that we know that, okay? So we know that there is a linear relationship in the data. We don't know what it is, but we do know it for some reason or other, because of the physics, or for whatever reason. So let's say we now want to learn from this data. We can do one of two things. So the first thing we could do is say, okay, I'm just going to fit like a generic unstructured neural network to the data. Okay, and we can do that, and we'll get some curve. Will look something like this, right? It won't be a straight line, but it'll do a sort of okay job. But I think what you'll probably agree is a much better thing to do is just to use the fact that we know that structure is in the data, and say, okay, well, if we know there's a linear structure in the data, then we might as well just fit a linear model to that, right? And use that information. So if we do that, we're going to get a straight fit, and this is going to be a better fit to the data, and it's going to give us lower generalization error, right? So yeah, again, this is what I'm saying is very obvious, right? Just if you know something about the data, then put that into your model. And when you have a structure like this in a model, this is an example of something called an inductive bias of the model. Inductive bias because essentially it biases the model towards particular data sets, which in this case would be towards linear data. Okay, and this concept of inductive bias is extremely important in machine learning. So I guess many people know about convolutional neural networks, and these basically encode an inductive bias, which is related to translation symmetries of the input data. All right, so you've got images of cars, you shift some pixels to the right or the left, they're still cars. Right? So this is a translation symmetry of the input data. And what happens in the CNN is that structure is encoded into the structure of these convolutional layers in something which is called equivariance, which I won't go into details about. But the principle is the same, right? You encode the structure into the neural network in a clever way. And because of that, this is the reason why CNNs perform so well on this type of data. A similar thing occurs in transformers, where you have this self-attention module. So this is a similar sort of thing, but now the structure of this network is basically tuned towards permutation symmetries. So these things work very well on data where it doesn't really matter the order in which the elements of the input vector are given. Okay, and we all know how well these sort of transformer type architectures are at a whole host of things. And yeah, more generally, this approach can be understood in this framework of what's now called geometric machine learning, started by, I think, this paper in 2016. And yeah, within quantum machine learning now, classical machine learning, there is quite a lot of work trying to figure out what are the different types of structures and symmetries you can encode into neural networks, and what is the best way to do this, and so forth. Okay. Okay, so yeah, I hope you'll agree that this sort of thing is super important, and because it's super important, that implies a question for quantum machine learning, and that question is what types of inductive bias can be encoded, let's say naturally, into quantum models. And I would say we're not particularly short on answers to this question. So there are papers in QML where people have proposed specific architectures which are designed towards specific types of data. So, for example, these quantum graph neural networks for graph data, generalizations of CNNs, right, for translation invariant data. This is a recent one for permutation, symmetric data. And so, and many more, I'm sure. So we have all of these different models which have these different structures, which is cool. And I think this is a super interesting, important thing to do. However, I think there is still quite a big elephant in the room, which is the main question I want to tackle in this work. And that question is, well, okay, yeah, we can put all these biases into our models, but actually the big question is which kinds of bias are actually hard to emulate classically, right? Because in the end, that's what we care about. We want a model which you can't just reproduce with a classical one. Okay, so this isn't a particularly easy question to answer. And the way we tried to answer this, perhaps unsurprisingly for me, is to look to quantum foundations. And in particular, we study something called contextuality, which maybe you've heard of. And what this is it's a very commonly studied form of nonclassicality in quantum foundations, which goes back actually many years now. The reason why you might know it is because within quantum computation, it's been connected quite a lot to advantages, so for the sort of necessity of quantum advantage. And in fact, to have sort of a quantum advantage, you sort of need contextuality to be present. And to be a bit more specific for people that know more about this, we actually study something called generalized contextuality, which is, if you like, a version of contextuality that was introduced in 2005 by Rob Speckens. And this is generalized in the sense that it captures all the sort of other previous notions of contextuality in one sort of framework, which I'll explain. But yeah, so the main reason for doing this, right, why do we look at quantum foundations? Well, basically our key motivation is that, well, if we can understand the structure of contextuality in a machine learning setting, right, then this might suggest biases which are hard to emulate classically, precisely because we expect things that are hard to emulate classically to be connected to contextuality. Okay, so this is sort of how we want to get to classical hardness is through this route of contextuality. Okay, so this is like sort of a graphic for the sort of big picture result I want to explain in this talk. So the first thing that we'll have to do, and that we did in this work, was to basically combine machine learning and contextuality to create this common framework so that we can talk about both of them at the same time. So I'll explain that. And then, as I said, the main thing I want to lead towards is to explain this link between these two concepts, one of them being inductive bias in machine learning, the other one being this thing called operational equivalence in contextuality that I'll get onto shortly. And yeah, once we have that, there'll be this sort of main result, which is the following. What it says is that if I have a machine learning model that has an inductive bias for data with a conserved quantity, okay, and I'll explain more later in the talk exactly what I mean by data with a conserved quantity. For now, I'll just leave it like that. So if I have a model which is biased towards this type of data, and then what's more, if I add non-contextuality, so I enforce that model is non-contextual. And just a reminder, because people get confused with this, non-contextual is like classical, okay, and contextual is non-classical, so it sort of goes the other way. Right? So this is adding a notion of classicality. Okay, so I take my bias model with this particular bias, I enforce this for a form of classicality, and what we see from that is this limits the expressivity of the model, okay, which then can impact potentially learning. Okay, so that's that's going to be the sort of main result I want to get to by the end. So if you remember nothing else, try and remember that. It would be a crime to go on without mentioning the other, I'd say, two works connecting contextuality and quantum machine learning. So the first of these, enhancing generative models via quantum correlations, and the second one, which was recently published in PRX Quantum, interpretable quantum advantage in neural sequence learning, by some of the same authors. And I think one of these two papers was even recently presented in this seminar. But I won't say any more about those in this talk. Okay, so this is the structure of the rest of the talk. I'm now going to spend quite a bit of time introducing and explaining generalized contextuality. I basically have three tasks, which I've put as these three bubbles. So I need to explain what an operational scenario is, then what this important concept of operational equivalence is. And finally, I have to explain something called an ontological model. And once I have those three, hopefully it will be clear what non-contextuality is in this framework. And then once that's done, we can move on to the machine learning. So it's going to be then quite straightforward to define what we mean by a contextual learning model. And from there, this result, which links inductive bias to contextuality and then expressivity, will hopefully be clear. Okay. So let's start with the operational scenario. So an operational scenario, basically you could just call this a scenario. Okay, I'm borrowing words from contextuality to be consistent, where they typically put operational in front of things. But yeah, by all means, just think of this as a scenario. And this is basically just a sort of the learning scenario that we work in, and it's the following. So we imagine we have a machine learning model, which is this yellow box in the center here. And we can do one of two things to this model. Okay, the first thing we can do is we can input some data X into the memory of the model. Okay, so for example, if my model was a classical neural network, this would just involve setting the first layer activations to the values of X. But if my ML model was a quantum machine learning model, right, this would correspond to, say, performing some data encoding unitary on the initial state of the model. Okay, so you see here, I'm not specifying anything about the inner workings of the model, even the theory. This is sort of a very abstract thing where I'm saying, I have a data point X and I can load it into the memory of the model, whatever that memory happens to be. The second thing I can do is I can query the model for some predictions. And I have a choice here from a number of tasks I'm going to denote by K. So I have more than one task. And so technically that means we're working in something called the multitask learning setting, which you can read about more online if you're interested. The reason we do that is because it's easier to connect sort of results in contextuality to machine learning in this way. In the paper, we do explain how you can also work in sort of a single task, let's say more standard setting. But it's a bit of a subtle point to go between the two, and it's clearer to work in this multitask for this talk. So in the rest, I'll just be working in the multitask setting, but check out the paper if you want to see the single task. Okay, so I can do these two things to my model, and then once I've input some data and I've queried with a task, the model is going to output some label, which I denote by y. And so basically in this scenario, right, my model is completely described, at least on this operational or observational level, by a set of probabilities that I write P sub k for the task, probability to see label y, given input x. Okay, and these things in contextuality are called the operational statistics because they refer to what you do operationally to the device. But yeah, if you like, just think of them as statistics. Okay, so that's the setting, the sort of learning setting that we're considering, or the sort of the model, let's say. Next, we have this notion of operational equivalence. Okay, so operational equivalence, yeah, again, it's a bit of a mouthful, but you can just think of it as indistinguishability because that's basically what it is. It is a specific type of indistinguishability. And to explain it, let's imagine I do the following now. So I have a coin. It's a two-sided coin, and it gives heads with probability P1 and tails with probability P2. And so I flip this coin, and then conditioned on heads or tails, I enter either the input X1 or the input X2 into the memory of my model. Okay, so basically this is just a stochastic data loading, essentially. So I do that, and then I'm going to look at the behavior of the model when I ask it for tasks, and it gives me labels, right? And I hope you can see that if I do that, right, the statistics, the probability to see y given task k, and given that I've input this mixture of inputs, this is just going to factor out into the sum of P1 times what happens when I input X1 plus P2 what happens when I input X2. Okay, this is just sort of standard probability theory. And I can do the same thing now, just replacing my X1, X2 by some different data points, X3, X4, and using a different coin with probabilities P3, P4. And again, I'll have the probabilities are just given by the corresponding sum. Okay, so these are two different sort of stochastic data loadings I can do, essentially. So then what is operational equivalence? Well, we would say that there is an operational equivalence if the two mixtures are indistinguishable. Which means, right, if I look at the probabilities given the first mixture, then these should be the same as the probabilities given the second mixture, and this should be true, right, for all possible tasks I could ask and for all labels I could get. So what this means is from the perspective of a user which is just querying the model but doesn't know about the data input, essentially, there's no way to tell which of the two cases you're in, right? So hence the indistinguishability. And I will denote this by this squiggly notation, right? So this basically says this mixture of inputs is operationally equivalent to this other mixture. Okay, so that's operational equivalence of inputs. But it turns out, sorry, before I move on, I'll give an example to hopefully make it a bit clearer. So let's now imagine we have a specific learning model, and it's going to be a quantum machine learning model. It's going to be a very simple one where the memory is just a single qubit. Okay, so data loading corresponds to preparing the qubit to some state, and a task corresponds to measuring that qubit and getting some outcome from the measurement. And so let's, on top of that, imagine that we have some 4 data points, x1 to x4. And when I enter these into my model, these just prepare these 4 qubit states. Okay, so either 0 or 1 for x1 or x2, or plus or minus for x3, x4. Now, if I do this, right, what you'll notice is if I now do a stochastic data loading of x1 and x2, right, that means I'm going to be preparing on average the average of the states 0 and 1. Okay, and then that state is, of course, just a maximally mixed state. However, that's exactly the same as if I were to mix the inputs x3 and x4, right? Because now I'm just decomposing the identity in a different basis. Okay, so both these two things result in the same state in the device, the same density matrix. Therefore, they are indistinguishable with respect to all the tasks. right? So if this is my specific model, then there would exist an operational equivalence between the equal mixture of x1 and x2 and the equal mixture of x3 and x4. Okay, so that's operational equivalence for inputs. But we can also define it for tasks, and the process is very similar. So now, again, I've got my coin, but this time when I flip it, I'm going to assume we have something loaded into the memory of the device already. And I'm going to query for either task K1 or task K2 with the corresponding probabilities, getting some label Y, okay? And, for the same reasons, right, if I now want the probability to see label Y given a specific X and given this mixture of tasks, then again, this is just going to factor into P1 times what happens when I ask task K1 plus P2, what happens when I ask K2. And once again, as before, right, I could consider different tasks, K3, K4, different probabilities. And again, my statistics would just decompose in the same way. Okay, so now we can talk about operational equivalence of the tasks, and it's a little bit different. We say that there is an operational equivalence, right, if the event of seeing a label Y is indistinguishable from the event of seeing a potentially different label Y prime. So mathematically, what does this mean? It means, okay, if I look at this probability that comes from the mixture of K1, K2 for a label Y, then this should be the same as the probability of my other mixture for label Y prime. And these probabilities should be the same no matter what the input was for all X. Okay. People can get a bit confused here because I've got different labels. So, it's almost like they are distinguishable because you have two different labels. But here the point is really it's the event which is the same, right? So the event of seeing Y for this first mixture always occurs with the same probability as the event of seeing Y prime in the second mixture, so that those two events are basically statistically the same thing. Hence, that's the sort of indistinguishability. Okay, and similarly to before, I'll write this with this squiggle, using this notation with the square brackets to denote seeing level Y given task K1. Okay, I think that one's it's a bit trickier, but it's actually the most important one for this work. So I'm going to give another example. And sorry, before I do that, I'll just say these definitions also extend to mixtures with more terms, right? So if I had a mixture of 3 tasks, which actually I'll explain now, I would have the corresponding thing with just 3 things here instead of 2 on either side. Okay, so this is an example of a operational equivalence in a model related to the tasks. Okay, and for this setup, I'm going to need 3 tasks. Okay, and again, we're going to imagine our model is a QML model with a single qubit. Okay, so now again, my input states correspond to qubit states, and my task corresponds to qubit measurements. And in particular, I'm going to assume that my measurements have a very symmetric structure. So this here denotes a plane of the block sphere. So for task K1, right, I'm going to assume I'm measuring in this black direction here. So if I get this projector, it corresponds to seeing a label 0. If I get this projector, it corresponds to seeing a label 1. And the other 2 measurements are symmetric, right? So the measurement for task K2 is going down this direction, 2 pi over 3. And for K3, again, another 2 pi over 3 in this direction. Okay. So let's say I have a QML model with that specific structure. Okay. How do we see there's an operational equivalence? Well, one thing I can do in this model is I could flip a 3-sided coin, right, with uniform probability, and query the model for one of my tasks. Okay, so let's say I do that, and then let's say also that I just look at the probability to see the label 0, given that I do that. Okay, so here I've just highlighted the corresponding sort of projectors for outcome 0, given the 3 tasks. And hopefully what you can see, right, if I average these 3 things, which is what I'll have to do, I basically just get a measurement operator, which is proportional to the identity. It's the identity over 2. And what that means is if I do mix these three tasks in this way, then no matter what my qubit state actually is, so no matter what the input is, I'm going to see a probability of 0, which is always 1/2, right, independently of that input. So I've sort of averaged everything out. And then we can look at the same thing for the outcome 1, for the label 1. Okay, and you see essentially nothing's changed. I've just rotated things, but again, by symmetry, my measurement operator is going to be the identity over 2. So I'll again have this condition that the probability to see the label 1 is 1/2 for all inputs in this specific model. So you see, okay, I've got something which is happening for the same probability for all inputs. So this is exactly an operational equivalence, which we would write as this, right? Saying if I now mix task 1, 2, or 3, looking at label 0, this is operationally equivalent to if I mix, again, task 1, 2, or 3, and I look at the label 1, okay? Okay, so that's an example of operational equivalence for tasks. It's actually going to come up again later, so bear it in mind. Okay, and now finally I can talk about what an ontological model is and then what contextuality is. Okay, so an ontological model, if you've heard of something called a hidden variable model, it's essentially the same thing. So you can think of that. And what it is, it's a very general description of the sort of physics which is happening inside the device or the model. Okay. So what we say is the following. We say, okay, so I come in with some input X, and what I'm going to assume is when I input that X into the model, this prepares some probability distribution that I write mu sub X over a set of physical states that I call lambda. Okay, and here I've got a finite number of physical states just for simplicity, but it could be a continuous set as well. And so, right, to give some examples, right, lambda could just basically denote the different weight configurations of a neural network. Okay, that would be some other physical states. So that when you come in with an input X, right, if your neural network is sort of deterministic, that corresponds to just like a delta on a particular weight configuration. But if you have a stochastic neural network, that would be a probability distribution over these different possible weight configurations, which represent the sort of the underlying physical state of the model. But if you had a quantum machine learning model, right, these lambdas would represent, say, the possible pure states that the model could take. And then when you input X, right, a mixture of these would correspond to some density matrix that the state is in. But I mean, these are examples, but it actually doesn't matter because this thing is very abstract. All we're saying is that there is a set of physical states. We're not even sure what they are, right? And when we input X, the result of that is to prepare a probability distribution over them. Okay, that's really all we need. Okay, so then the second thing we assume, not even sure if it's an assumption, it's very general. We say, okay, if I now come in with a task K, and my device is in a physical state lambda, then there is some function which we'll call psi sub k, which just tells me the probability to see the label y given the physical state is lambda. Okay, so there is some function which does this. Again, to go back to our examples, psi, for example, could be the softmax function at the output layer of a neural network. Because this softmax function typically gives you the different probabilities of the labels, right? But in a quantum machine learning model, this is basically just the Born rule, right? Because the Born rule is the thing which tells you how to translate quantum states to probabilities. But again, in this model, we're not specifying anything. We're just saying that there exists some function that does this. Okay, so if we put all of this together, we now want to write down an expression for the observable probabilities. So these, what we actually see in practice, which is P sub k y given x. To get this right, we just have to average over the possible physical states of the device, right? So we take our probability distribution over lambda conditioned on x, and then for each lambda, we condition that on seeing y given task K, we average over lambda, and this is what we see sort of on average at the observational level. Okay, so that's an ontological model. So what is non-contextuality? Okay, so we say that a non-contextual ontological model is one that satisfies the following implication, which is operational equivalence. So this type of indistinguishability we saw before should imply something called ontological equivalence. Okay, so sorry for yet another term, but hopefully this will be explained by this equation. So what this means is, let's take the example of inputs, right? So let's say we have this operational equivalence between these two mixtures of inputs. So what this ontological equivalence says is that it says, okay, well, if we take that same mixture, but at the level of the lambdas, okay, so now we mix the corresponding probability distributions in our ontological model, then these two mixtures should be the same for all lambda. Okay, so these mixtures should give the same probability distributions over the lambdas. Okay, so this indistinguishability here translates to an equality at the level of the model, which graphically could look something like this. So let's just imagine all these p's are 1/2 for now. Now I could have these 4 different distributions over lambda, and what this constraint is saying is that basically if I mix mu1 and mu2 to get this dotted distribution, then that should be the same as if I mix mu3 and mu4. Okay, so it's a constraint on what these mu's can be, because they must satisfy this sort of thing. And yeah, we can do then the same thing for the tasks. So again, if I have an operational equivalence between these two mixtures of tasks, then what this says is that, again, if we go down to the level of the model and we work with the size, the mixtures of the size should also be the same for all lambda. And you might wonder why, what was the point of that? Why are we doing it? So what this is a sort of Occam's razor explanation of what we're seeing. Okay, so what we're seeing at the observational level or the operational level are these indistinguishabilities, right? Things look exactly the same no matter what we do. And so one natural way to explain that is to say, well, okay, the reason why they look the same is because at the level of the actual physics, right, so the level of this lambda, whatever it is, they really are the same, right? The reason your mixtures of inputs look the same is because actually they correspond to this same dotted distribution over the lambdas, okay? So it's sort of, and the same thing for the tasks, right? So it's sort of a natural way to explain why you're seeing these indistinguishabilities. However, it's not always possible to do this. So actually quantum theory violates this, right? So that there exists probability distributions that you can generate using quantum systems, which have operational equivalences, but for which it's impossible to construct an ontological model, which is non-contextual, so which satisfies these conditions I just said. And interestingly, this usually coincides with sort of non-classical phenomena. Okay, so Bell non-locality, Cocker contextuality, if you know about that, doing well at basically state discrimination, optimally cloning things, and probably some more stuff by now. This has all been connected to the violation of this principle. Okay, so that's why it's sort of considered non-classical. And yeah, one thing which maybe is also clear, generally speaking, right, the set of non-contextual probability distributions is a subset of the contextual ones, right? So if I represent my set of distributions in some high-dimensional space, then what sort of happens is I get a polytope, and there's a sub-polytope of that which corresponds to the non-contextual distributions. And just a reminder, non-contextual, remember, means classical, not the other way around. Okay, so yeah, that was a lot of information, a lot of it probably new, so hopefully some of it stuck. And now we can move on to the machine learning. Okay, so now I'm going to define or explain at least how we defined what a contextual learning model is. And this is maybe perhaps already obvious because it basically just follows from the previous slide. So we define a learning model, which is defined by these probabilities P to be contextual if and only if the statistics cannot be explained by a non-contextual ontological model. Okay? Given the operational equivalences that exist in those probabilities. So this is just sort of most obvious, straightforward definition given what we've saw. I do want to make a couple of points which confuse people. So the first is that classical models can still be contextual. Okay, it's not that if you're contextual, it's impossible to simulate classically. I mean, this is hopefully clear because this definition only depends on the observed probabilities P, right? So if I simulate a contextual quantum experiment on my laptop, that's going to give me exactly the same P's. So, it's going to be contextual according to this definition. The point really is that what we expect is that contextuality implies some sort of simulation cost, right? So if you have a model which by some measure is very contextual, then what we expect or what we hope is that the corresponding classical simulation is going to be very expensive. Okay, so it's not that classical models can be contextual, but it presumably comes with a cost. Okay, this is reiterating what I said before. You can also define this in a single task setting. If you're interested in seeing that, please check out the paper. Okay, so finally, we can move on to the main result, the main link, and that is linking inductive bias and contextuality. Okay. So to explain this, I'm going to imagine a specific data set, but hopefully you'll see how this can generalize to other data sets. So let's imagine we have some input data points xi, okay, some vectors, and we have some labels that I'll call y1, y2, and y3, and these are generated via some conditional process that I write as calligraphic P of y1, 2, 3 given x, okay? And we're also going to assume that these labels take values plus or minus 1 each. Okay, so here basically my data set just consists of pairs of these inputs xi and this corresponding 3 labels that I'll write as vector yi. So what is the task? So imagine we have a bunch of this data. So we have 3 tasks because it's a multitask scenario. And the tasks are to sample from the 3 marginal distributions, p sub k, yk given x. Okay, so for task 1, you have to start sampling from this variable, this first variable y1, given that I give you an unseen x here. For task 2, it would be the second one, and for task 3, it would be this third one. Okay, so these are the 3 tasks. They're not completely independent because the data generation process can be correlated here. Okay, and we're going to assume, what's more, that it's correlated in a specific way. So this is going to define some sort of data structure. And what we're going to assume is that the labels that you get here, they contain a conserved quantity on average. So mathematically, what I mean by that is that if I look at the expectation value of y1 given an x, and I sum that to the expectation of y2 and y3, then what I'll see is no matter what my input x is, the sum of these values in expectation is always 0. Okay? So in that sense, it's like you have a conserved quantity in the data. And I mean, you could extend this for more variables and even to be sort of non-dichotomic, but for simplicity, let's consider just these 3 with plus or minus. Okay, so that's the structure of the data that we're going to consider. Where would this show up? So, perhaps an obvious place it might show up would be in quantum theory, where you have conserved quantities, right? If each of these expectation values, you see it as, say, a trace of 3 terms that appear in Hamiltonian, then if your states, for whatever reason, correspond to states which all have the same energy, then this sum will basically just be an expression of energy conservation in the system, for example. But interestingly, even outside of quantum theory, this sort of stuff can show up. So if you think of zero-sum game scenarios, here, essentially, you have a sort of conserved quantity, because if somebody wins something, right, the other players must lose the same amount. Okay, so there is a zero-sum condition. So if you consider sort of stochastic zero-sum games, then it's quite easy to come up with data sets which basically satisfy this sort of thing, reflecting the fact that the payoffs must be zero-sum. And in the paper, we talk a bit about some other possible data sets, but I think there's much more work to be done here. But essentially, whenever you have a scenario where you have a discrete conserved quantity, you can imagine how this sort of thing could show up, right? So potentially substance diffusion, maybe in biology or something, where you've got some molecules or particles which are diffusing but conserved. Manufacturing logistics, where maybe you have a conserved resource which is being used, or population modeling, whether people are conserved and so forth. Okay, so I think it's an interesting question to think about when this sort of constraint shows up. Okay, so let's move on to the main link. So this is how it goes. So let's imagine we have a data set with this structure. Okay, going back to the very first slide of the talk, right? What did we say? We said, well, if we want to learn this sort of data, it's a very good idea to use a model which incorporates that structure. Okay, so in particular, we're going to want our model, our learning model, to also respect this condition, right? And if I translate that into a constraint on the probabilities of the model, this is what I get, right? It just says that if I sum the probability of plus for the 3 tasks given an x, this should be the same as the probability of summing the probability of minus for the 3 tasks for all x. Right, so this is just encoding this bias into a model. But what you can now see, right, this is exactly of the form of an operational equivalence with respect to some tasks, right? Because if I put a third in front of either side of this equation, right, what this basically says is just, okay, if I mix the 3 tasks and I look at the probability of plus, then that should be indistinguishable from mixing the 3 tasks and looking at the probability of seeing the label minus. Okay, so the bias which has been coded from the data structure has been translated into an operational equivalence of the model. And then because of that, if we go through now and we apply non-contextuality, so this classicality, as we saw, this sort of thing implies constraints on the model probabilities. And the crux of that is that these constraints are they're gonna constrain the expressivity of the model, because you won't be able to sort of do everything, essentially. Okay, so that's how we get that's how we make this link. I will say very quickly that actually, I mean, large expressivity is not always a good thing, right? Because if you have a very expressive model, then what's going to happen is you're just going to overfit your data. Okay, so it's not always good. But the point here is that actually, because we're considering models that have that specific bias, what you get with contextuality is more expressivity, but within the relevant bias. And this might be desirable in practice. So, if you take the case of like linear models, right? Generally speaking, you want your linear model to be able to fit any linear relationship, right? But say not a quadratic one. So if you have a linear model which is constrained, to just hyperplanes in some subset of the space, then typically you would say that's not a very good thing, right? You want greater expressivity within the particular bias that you care about. Okay. But yeah, this is a subtle point, I guess. Okay, I haven't got so much more time, so I'll be reasonably quick. So in the paper, we give a specific example where we work everything out. So it's very concrete. It's a bit of a toy example. So we sort of set up a data set which corresponds to this rock, paper, scissors game. So it's like three people playing this game with a referee. And because this game is zero sum, that allows us to construct one of these data sets, which naturally has this bias that we want. And from that, we can really go through and work out the precise details about what the constraints are on the expressivity of the model, which, yeah, in the end, ends up looking like this figure, which I won't be able to really explain in detail now, but if you want to see precise details, please take a look. Okay, so I think I'll conclude. So I think maybe one of the main messages of this work is that it is a new way to think about advantage in quantum machine learning. So this is not the usual perspective of looking for asymptotic complexity separations. And I'll just leave the question as is a foundations approach actually going to be more fruitful to find problems of practical interest? Right? Because if you go down sort of the complexity route, typically what you get is problems which are highly specific mathematical structure, and it's not really clear if those sort of structures appear in real world data. Whereas the foundations approach, because you're not trying to prove something so precise, it might be a sort of a better path to go down to get more general structures. Okay, so yeah, I just said that we present like a toy example in the paper, but I think a very interesting question is, can we actually find real world data sets that have this bias and seem to require a lot of contextuality to learn, according to our definition? I think this would be super interesting because it would give a potential example of a data set which had a real practical quantum advantage. And also a very important question, which I've not touched on, is just how hard is it to classically encode this inductive bias that I mentioned, right? So in the paper, we show that the bias can be reasonably straightforwardly encoded into quantum machine learning models. And this is basically just following the linearity of the Born rule. That's what it uses. However, I mean, if you try and do the same thing in neural networks, you have a bit of a problem because you find that the non-linearities of the activations in the network actually make it sort of non-obvious how to always satisfy this bias. And at least myself, when playing around and sort of trying to do this in a non-quantum model, I haven't succeeded. So to me, it seems a bit difficult to do this, and it seems that quantum machine learning is very well suited to this bias. But yeah, I'll be happy to be proved wrong. If you have some ideas, so please let me know. And so with that, I will finish the talk, and I'll be happy to take any questions. So thanks for your attention.
Yeah, so thanks, Joseph, for the very interesting talk. And yeah, you explained everything nicely. For the audience, if you have any question, then you can raise your hands or type the question in the chat, and I could help like ask the questions. And I see like Kishore raise his hands. Maybe Kishore, you can unmute yourself and ask question.
Yeah, thanks, Pengi, and thanks, Joseph, for the nice talk. So basically, contextuality, like you can simulate it using memory, right? I mean, so basically, when you say that the real world data set that require a lot of contextuality to simulate, do you mean that the memory cost of simulating contextuality, like that should be high? Is that you mean?
That is basically what I have in mind, because as you say, I think most of the previous results they typically do connect contextuality to memory cost, right? So I think that would be the most obvious thing.
Normally the memory cost is not that high, right? I mean, it's very like so far the examples that we know, like it's I mean maybe quadratic overhead or something. So
exactly, yeah.
So let's say the contextuality approach, like the quantum foundation approach is more like a information theoretic approach, quantum information theoretic approach. On the other hand, the complexity perspective is more like a computational approach, where like you are saying that the learner is not an arbitrary learner, but like a quantum learner, like it has some bounded like resources. And then so I'm wondering, like let's say via this contextuality approach, do you have any insight where like because of the contextual nature of data set, quantum can offer you exponential advantage over the classical case? Because it seems like like I mean, I can think about quadratic separations via this approach, but because it's it's basically we're asking about memory cost of simulation, right? I don't know, maybe in a distributed computing setup where let's say you are thinking about Bell non-locality, there I could think of like quantum foundation approach can giving you some real advantage, because there, like the number of bits of communication you can really limit, and you can say that no quantum model can in the distributed setup can learn on the classical model in the distributed setup can learn. On the other hand, the classical model, like can learn or something. I don't know, like what are your insights?
Yes. Yeah, my insights, I think, is a super interesting question, and yeah, we don't know. I mean, on the one hand, we know there are sort of exponential. There are situations where you do have a massive gap between classical and quantum in machine learning, and I would imagine that there is a lot of contextuality in those specific examples, right? So I don't imagine contextuality is not present there. On top of that, like there are examples of let's say contextuality inequalities, just so that these sort of inequalities you get which separate the two sets, for which you have like an exponential advantage with dimension for quantum systems. And so you do have specific examples where this does blow up a lot. I expect
actually I was
that the previous results haven't been connected to these, but to weaker ones.
Sorry. So my second question was something related to that, actually. Same thing. So let's say, like, I mean, here I cannot see the graph theoretic approach, but I don't know whether have you thought of relating it with the graph theoretic approach to contextuality. And there we know that there are graphs for which the lowest theta number divided by the independence number of the graph grows, like unbounded, like, so like for those scenarios, like, maybe one can like get some strong separation between quantum and classical. So my question would be, like, do you see any insight, like how this can be related to graph approach to contextuality? Because there I can construct like more and more difficult
Yeah, no, I've thought a bit about this. The challenge is always taking one of these proofs which are very specific and have very precise structure, and somehow turning them into a learning problem which is actually relevant somehow, and not just a rehashing of the mathematics. I'm not sure. One approach I wanted to go down was there is this phenomenon called anti-distinguishability, which has appeared in contextuality proofs. I won't explain it, but it's like the opposite of distinguishability. You sort of want to get the wrong answer. And there's exponential violations of inequalities related to that. But that anti-distinguishability, you could imagine somehow it could be translated to a sort of bias that you want in some data set. I tried a bit, but without really satisfying connection. But I mean, basically, I don't know, but I think it would be interesting to think about this.
Okay, yeah. Thanks for Kishore for asking the interesting questions. And yeah, thanks for Joseph for giving a very nice answer to those as well. So okay, maybe again, I'm not an expert in contextualities and quantifications, but maybe this question might be a bit stupid. So over here, like you are considering the supervised machine learning settings, right, where you have label data. And would it be possible to extend the framework to unsupervised machine learning? And like, would there be a kind of a concept of like contextuality in terms of like unsupervised machine learning? Okay, I'm not too sure how to formulate.
That's a good question.
Yeah.
Yeah, if you don't have labels. Well, I probably could be done somehow, because I mean, even in unsupervised learning, you want to create the labels yourself, right? So labels, they will show up at some point.
But basically you will try to learn the probability
distributions
and I don't know. Yeah.
I have the feeling that if you completely remove the labels, you're not going to get the contextuality. I think you would probably need them. Yeah, just to define even operational equivalence, you need to sort of have a non-trivial set of things you can look at. So
right. Okay.
Yes, it would be difficult, but not necessarily impossible if you introduce labels.
I see. Because it would be kind of interesting to learn of like some contextual probability distribution per se, and trying to see how the classical model can learn versus like how the performance is for the quantum models. Okay, thanks, Joseph, for to answer that. I think now
Thank
we
you.
are kind of running out of time, and perhaps we can end the seminars like here. So thanks again, Joseph, for like giving the very interesting talk and kind of like now be clear on like what could be some other way of thinking in terms of advantage in quantum machine learning, and perhaps this work could inspire people to go pursue in this direction instead of the usual complexity arguments, trying to prove separation between like quantum and classical machine learning on some like artificial tasks. Yeah. So if you guys have any questions, I guess you guys you can email like Joseph and ask about questions. If not, then we can end the seminars now. And thanks Joseph again for giving the interesting talk. Yeah. See you guys.
Thank you. Thanks everyone.